Dear Heavenly Father, we thank you for this day. I thank you for these students. Just pray to be with us today. Help us to just wrap up our thinking about fractional linear transformations. And I just pray that you be glorified in what we do here this day, Lord. In your name I pray. Amen. Okay, so I started to calculate to show you that circles map to circles under, man, that's bright, inversion for me. Not for you guys so much, but yeah. You can point it up towards the ceiling. Maybe that would give us more diffuse light. Yeah, like just, yes, not the camera. Very good, not the camera, yes. That's funny. Anyway, Churchill's complex variables. So many of us have learned out of this book. Not you guys, obviously, but the older generation. For example, your beloved Dr. Sprano had a course out of this, I think. But in here, there's a section just on the reciprocal function, and there's about 2 pages devoted to showing that circles map to circles. I can't find it, but I'll probably make you a copy and send you a PDF or something of those 2 pages. It's technical, but I can kind of explain to you a few of the basic rudiments of it. Oh, come on, tell me I didn't bring any markers. Well, you didn't have to actually say it. Oh man, I don't have, what on earth? I do not have a single stupid marker with me today. How annoying is that? And I was so clever, I got the markers that I've been carrying around in my bag out of my bag the other day. Oh.
Like how I did that one time with that problem.
Why do you have some too? Like Michael.
Thank you, Lorenzo. I will replace these.
Because they never have any good whiteboard markers.
Ooh, purple. How exciting. Okay, before I get back into that, I just want to carefully define something for you. So what's a neighborhood of infinity? So an epsilon neighborhood of infinity, a disk around epsilon would be this. Z in the complex plane, such that what? What does it mean to be close to infinity? It means you're really, really far away from zero. Right, so how to capture that is just 1 over the modulus of z being what? Less than epsilon. So a neighborhood of infinity is actually an exterior annulus. So it's something like, if I look at, say this is epsilon, then neighborhood of infinity is like this guy. Everything out there. The great beyond. And just a little bit more of, how would you define a limit as z goes to infinity of f of z is equal to L? What would this mean? I'll start us out. For each epsilon, there exists a delta greater than 0 such that what? If the modulus of z is greater than 1 over delta, that implies modulus of f of z minus L is less than epsilon. In other words, you can pick an exterior annulus such that you can make the function as close as you like to the limiting value on all the points in that annulus. This is exactly the notion of limit where you've replaced an open disk with an exterior annulus. Now, pragmatically speaking, that's kind of a drag, right? So another way you could look at this, there's a dual thing. You could say that's the same as saying, well, that's really just looking at the limit z going to 0 of what? F of something equals to L. I'll leave the proof of this as an exercise for you guys, but what do I put there?
1 over z.
Yeah, exactly. So there's this duality between limits of 1 over z functions going to 0 versus z going to infinity functions of z. I mean, these are they're dual descriptions of the same math. Now you can also talk about limits being equal to infinity, right? What does it mean? What would we mean by definition limit as z goes to, say, z naught. F of z equals to infinity. What would that mean?
There exists, or for each epsilon greater than 0,
Mm-hmm.
there exists a delta greater than 0, such that the modulus of z is greater than 1 over the symbol, the name of which, delta. That's it.
I think, well, let me write down.
It implies that
Mm-hmm.
f of z minus infinity.
Well, how about f of z minus, f of z is greater than what? 7. Joe? You're contaminating this class from beyond.
Wait, who's Joe?
Joe Colombo is in my advanced calculus class, and he's been advocating the use of 7 as a variable this semester.
Oh, right.
That's the guy that's in your office.
That is the correct reaction, Malia. It's ridiculous, yes. Is he in my office? Yes. Well, sometimes. That's not exactly a clear descriptor, like a person who was in my office, yes. I mean, yes, he was in my office. That is true. Just 1 over epsilon, right? In other words, the modulus is unbounded. You can make the modulus as big as you want by getting as close as you like to the limit point. That's what it means for the limit to be infinity. So this is that, and so, for example, some things you could do like, what is the limit as z goes to infinity of 1 over z? What's the limit as z goes to infinity of z? What's the limit as z goes to 0 of 1 over z? I mean, you can work out from these definitions that the obvious things are true. In fact, this is 0, this is infinity, and this is what? It's also infinity, right? There's an example. The last 2 things I wrote is an example of this duality. This is also true when L is infinity. You can combine, mix and match these concepts, right? So then if you have more complicated examples, like say the limit as z goes to infinity of z squared plus z over 3z squared minus 2, you can do things like, okay, so that's going to be the limit as z goes to infinity of 1 plus 1 over z divided by 3 minus 2 over z squared, right? And once you know that 1 over z goes to 0 as z goes to infinity, then you know that you can basically apply limit laws. The fractions go to 0, right? And you get what? Yeah. In other words, those kind of, well, I would say hokey steps, but I admit I'm using hokey in a derogatory sense, which may be objectionable to some of you. But it is, after all, an objectionable and derogatory term. Sorry. You pick the sports teams you want to root for, whatever. But, those formal calculations I was doing last time are supported by these limits, all right? That's all I'm saying. So let's get back to the problem of the inversion. So, again, C star is what? Complex union with this point at infinity, right? So-called one-point compactification of the plane, because it has a one-to-one correspondence with that Riemann sphere, which is compact. This is actually one example of a more general topological construction called by Alexandrov, which you can study in topology when you study that. But anyway, here, focus. So I wanted to think about the function 1 over z, right? And f of z is equal to 1 over z. So if you want to think of that as being w. And what I wanted to show or argue is that if I've got a circle here in the z-plane, what happens? It maps it over to either a circle or a line, I'm not sure what, in the w-plane. So I'm advocating this view that lines are circles as well, generalized circles. in the extended complex plane. This is a viewpoint we can take. Because lines have constant distance from infinity. Circles, maybe. Huh. I don't know, that was an intuitive comment I was trying to add. You can ignore it. Okay, so. You know, we should look at some specific examples. So it'll help you understand better what I was talking about last time. So first of all, what happens if I have a circle, right? And it's counterclockwise oriented. Say the radius is equal to 1/2. Right, here's the z-plane. What's that get mapped to over here? Under the 1/z mapping. Circle centered at the origin. What does it become? This we realized last time. We said this was easy. If we look at circle centered at the origin, you could see it's another circle, right? Of radius 1 over reciprocal radius, right? And the e to the I theta, or the e to the it, changes to e to the minus it. What does that mean? So radius 2, right? So the radius over here is 2. But the other interesting thing, if you look at it more carefully, is the orientation has been flipped, right? It's changed from counterclockwise to clockwise under the inversion. That's kind of interesting, right? Because if you look at the region which is inside the curve, right, how do we define the interior of a closed curve? Remember, you imagine yourself walking along the curve, and whatever's to your left is inside. That's the convention. So if I walk along the original curve, what's inside? Just the disk, radius 1/2. What's inside here? Imagine yourself walking along. What's on your left? Outside, right. This is like that joke I like to tell about, an engineer, a physicist, and a mathematician are asked to enclose a maximum area, with a particular length of fence, and the engineer says, "I will make a square." We can put it into production. We can make lots of these. The efficiency is good, whatever. Of course, the physicist says, "I will make it a circle." A circle has perfect symmetry, right? Mathematician says, whatever, let's put it in any old shape, close it, and he says, "I'm outside." See, so he's, you assume that the fence is on the earth, so, this is the inside of the fence. This is mathematics of that. I have told that joke before in college algebra to get no laughter whatsoever. It just completely died once. I'm like, whoa. That's where I am right now. I'm alone in the world. Oh no. So I need to go watch some NASCAR or something and maybe study the sports. I don't know. Now, on the flip side,
Sports ball.
sports ball. On the flip side, if you had a circle that was larger than radius 1, right, it would collapse it to a circle smaller than radius 1. But anyway, you see you got circles going to circles. Another exceptional case that's interesting to look at is this one. What if I look at the circle in the z-plane centered at I of radius 1, all right? Where does that go to? Under the reciprocal mapping. See, here's the thing I should have thought of. You asked me last time, Sharon, how do you get lines from circles? The answer is very simple. If your circle intersects the origin, that means that the reciprocal map takes the origin to infinity, which is to say that you have a line in the W plane. So this circle maps to a line. When you work,
So like in the top example, that wouldn't map to a line.
no, this is a circle.
But it doesn't intersect the origin. It includes the origin.
I'm saying the actual circle itself intersects the origin.
Right.
That doesn't happen here. The circle,
It's not going to go to a line.
no, it's a circle.
Yeah. Okay.
Yeah.
I didn't know if like in another example it could.
No. Well, think about this. Okay, so if your circle doesn't intercept the origin, right? That means that the modulus of z is bounded. Just pick the outer point on the circle. That's a bound for the modulus, right? So then 1 over the modulus can't be larger than, I mean, it can't get too big, which of course is to say that it's not a line, right? Because a line, a line will go to infinity. It'll have infinite modulus, right? So if 1 over z is the image over here, if w equals 1 over z is the image, unless 1 over z becomes infinite in modulus, it can't be a line. And the only way it can become infinite is if the circle actually intersects the origin. Otherwise, the modulus is bounded, and likewise, the reciprocal of the modulus is... Well, excuse me, the modulus is non-zero, so the reciprocal of the modulus is bounded, is what I should say. This one, something really cool. I've thought about this a while, guys. If you look at the unit circle, right? I don't know if I'll be able to do this carefully enough, but if you look at the unit circle, it's very telling as to what happens with these reciprocal transformations, because the unit circle is fixed in a sense, right? If you feed something on the unit circle into the reciprocal mapping, what happens is you get something else on the unit circle, right? But not necessarily the same point, because you flip e to the it to e to the minus it, right? So basically, you're trading your standard angle for minus your standard angle, whatever it is. So if you think about that, this point, right? This intersection point of the, I'm thinking about mapping the black curve, okay? So let me give it a name. We'll call it sharing. Okay, so if you map sharing under the reciprocal mapping, for example, where does the point, well, we agree 0 goes to infinity. That's hard to picture. Don't start with that. But this point, where does that map to? Right. If you'll allow me to superpose the w and z planes here for a second, it helps me. So yeah, this maps to down there, right? So let's say a, this is 1 over a. And there's also this point over here, b. It maps to what? So like that. So the opposite standard angle is like, so it's down here. So those are 2 points on this thing. I'm telling you it's a line. So in fact, that's the transformed curve. But I can even tell you where it is. That's pretty easy because where does this point go to? Let's see, where was this point? Sorry, I'm thinking of something here. Well, what's this up here? This top point? I can be more explicit there. I mean, I could be more explicit about where A and B intersect the curve as well. I just don't want to get into the details. It's like plus or minus pi over 4, I think. I mean, pi over 4 and 3 pi over 4. But up here, what's this point? That's easier. Circle radius 1, 2i, right? So we reciprocal of that down here is what? 1 over 2i, or minus I over 2. So you see the image of Sharon, so if this is f of z.
Sharing.
F of share, oh yes, I'm sorry, f of sharing. F of sharing is a horizontal line. Right, horizontal line, y equals to minus 1/2. Yep.
I'm in geometry right now, so this might be like a little overboard, but like, does it give you a line and any 2 points form a line? And that's why this makes a line, like the 1 over b and 1 over a?
Well,
Or is that not?
just because I have 2 points, I could also draw a circle through 2 points. I need to know it's a line in order to say that the 2 points make it a line. I haven't proved that it takes lines to lines. I'm still claiming that. But I'm also claiming that the case when it goes to lines is precisely the case when your initial circle goes to the origin. Again, all of this is with respect to the reciprocal mapping, 1 over z, right? For a general fractional linear transformation, it's more complicated. You can use the cross ratio thing, map a triple of points to the other triple of points, whatever you want. So This is why when I got to the point of the cosine sine expression last time, I was like, I don't want to go further because I could sense that there was cases. There's lots of cases, and when you see the full proof of it in Churchill, you'll be kind of like, whoa. It involves, he actually breaks it up into the u and v components, look at the x and y equations. It's somewhat involved. But these are important cases anyway that I thought were useful to show you. So that's about all I have to say about those. Do you guys have questions about the quiz or anything? Not yet?
I will Monday.
When will we get
Well,
it
it's
back?
due at the start on Monday, so
Will we get it back at the end of this class on Monday?
that seems doubtful, but I will show you the solution to the quiz on Monday. So, unless I can make Daniel come here and grade it furiously in the back.
Can we not put our names on it and then put little signals
You want
make
to,
a symbol
you
that
guys,
is
you want to do,
unbiased?
you want to do peer grading? Oh, wait a minute. Oh, you want to hide? You want to be anonymous for the sake of the grader? I see.
I feel like my grade would be better.
Well, I see. I think the only way to really effectively implement that is to make all of you tech your homework. So you.
He hasn't learned our handwriting yet.
I don't know. Your handwriting is somewhat distinct.
I don't know. I think some girly guy handwriting.
It's definitely not mine.
Are we allowed to have this conversation anymore?
It might be.
Isn't gender fluid?
Yeah, I think
That's true. I might not be allowed to. Brave new world we live in, where you can't hold opinions anymore. Okay, so here's an example. We can try. This may or may not go well. We'll try it though. W equals to the sine of z. Let's see if we can't find an inverse to this function. Right, so I'm saying the function. I'm saying that this is f of z. And what I want to do is I want to find an inverse for f, but I haven't told you what the domain is yet. I mean, if the domain is all the complexes, we're definitely stuck because it's not one-to-one. So we definitely can't find a global inverse, right? But maybe we can find a local inverse. Maybe we can restrict the domain such that the complex sign is injective. So how'd you go about this? Well, let's see here. This is 1 over 2i e to the iz plus e to the minus iz is equal to w. Just generically speaking, your goal in finding an inverse function is what? What do I want to do? Solve for?
solve for x, y.
So f inverse of w is equal to what? Z, right? So I think somebody said it. You want to solve for z is what you want to do. When you do that, we'll probably discover the necessary restrictions on the domain in order to make this go. Right? Of course, we can also go back and look at the inverse function theorem. What did the inverse function theorem say? If the complex derivative is non-zero at a point, at least local to that point, there exists an inverse. When's the derivative of sine z non-zero? Actually, that begs a question that we haven't talked about enough in here. What are the zeros of sine? What are the zeros of cosine in the complex domain? Do you guys know? I mean, we've proved that sine and cosine are unbounded, right?
You could use the formula for the modulus of sine, right? And then set that
Ah, right. That's a very good point. You said look for where the modulus is 0, set that equal to 0. That's not a bad approach, because the thing can only be 0 if the modulus is 0. That's nice. It makes it into a real problem. I like that. Without getting into it here today, I'll tell you the answer. The answer is that the zeros of sine and cosine in the complex case are precisely the ones you already know. There are no new complex zeros. It's just the ordinary real zeros. It's just 0 on the real axis. Multiples of pi are plus or minus pi over 2, plus or minus 3 pi over 2, plus or minus 5 pi over 2, plus or minus 7 pi over 2. You know the drill. The drill. Drill? Sharon, you've corrupted my language. Let's see here. It's fun to make unprovoked attacks on Sharon. Let's see here. E to the iz. Oh, and you guys, come on, don't let me do this. What's that? Minus, thank you, yes. So e to the iz minus e to the minus iz, and I recommend we multiply by 2I. All right? Then what am I going to do? I need to solve for z. Now, you actually did something in Calculus 2 kind of like this, but you may have forgotten it. It may be a while since you've done this, but what I'm going to do is I'm going to multiply through by e to the iz. And that will give me e to the 2iz minus 1 equals 2iw e to the iz. And then I'm going to let's say eta equal e to the iz, right? So eta squared is e to the 2iz. And with that substitution, I have eta squared minus 2iw eta minus 1 is equal to 0. That's very nice. That's a quadratic. And we can solve that. So we solve it by completing the square. So you've got eta minus iw quantity squared. Let's see here, is equal to what, 1? So basically, I'm going to undo, put the 1 back on the other side again. And let's see here, I just added a I squared, w squared. So let's see, I had to do what? Yeah. So I think that means plus w squared, right? Do you guys agree or disagree?
No, that's right.
Okay. And then what? Then we've been through this before. Basically, the result of the solution to removing a square, it ends up that it's equal to plus or minus the principal square root, right? Certainly one solution is plus or minus the principal square root of 1 plus w squared. Understand that that is a shorthand for that, taking the square root of the modulus, e to the I principal argument divided by 2, right? That is the use of the square root symbol is referring to the principal square root. Okay. So then what's eta equal to? Eta is equal to I omega plus or minus the square root of 1 plus w squared. But of course, eta was what? Yeah, e to the, what did you say, e to the iz? Yeah, okay. So I can find all solutions by using what this says then is that iz is equal to the little log, or to be less, let me be a little bit annoying here. I'm saying iz is an element of the little log of iw plus or minus the square root of 1 plus w squared. And if you pick different branches of the log, you'll get different, different inverse sine functions. Yeah.
I think inverse sine is 1 minus w squared.
I think you're wrong. Let's see here. So if we multiply out eta minus iw squared, we get eta squared minus 2I eta w plus I squared omega squared, right? But this is minus omega squared, right? So I have subtracted, I say omega, I meant w. I have subtracted w squared by completing the square. So I have to add w squared to both sides, and that, it's right. All right, so if I want to say z is equal to, let's say, minus I, principal logarithm of w plus the square root of 1 plus w squared what domain of f have I picked, let's say chose, I think chose is better, chosen maybe, I don't know, whatever. Choosed. What domain of f is the above f inverse of z for? There, this is worse grammar, but more mathematical content. In other words, you know, what if that's the formula for the inverse function, what is my restriction of sign? What restriction of sign am I talking about? How do you figure that out? What's the key idea here? It's just basic function stuff, right? If this is the domain of f, right? Then if I look at f, where does it map to? The range of f, right? And where's the inverse? It goes back, right? So the domain, right, of the inverse function should be the range of the original function.
So 0 to 2 pi?
0 to 2 pi. I don't know. I have to think about it. I mean, certainly, what do we need for the what's the domain of? So let's say that this is f inverse of z. Okay. What's the domain of f inverse of z? That is, after all, that's where I made my choice. That's what we have to figure out to start with, right? What's the natural domain of that expression? One plus w squared greater. This is a principal square root. It eats complex numbers for breakfast. It's not a big deal. No problem.
The arc of w plus square root of 1 plus w squared is in between negative pi and pi non-inclusive.
The arc.
Because it doesn't like it's really complex.
I think that's. Well, that's what that will output, right? That might.
Oh, I thought that was the domain.
What is the domain of the logarithm? I mean, the principal log.
Bigger than
So you go back to the exponent. So what you're saying, I think from a right. Oh no. Sorry. I'm getting distracted. So what did you guys say? What was the domain of the principal logarithm?
bigger than 0.
Right. Yeah. That's one answer. It's the the punctured plane, right? Everything except for 0. If I want it to be, I think I felt like no, I don't have to throw out any. I'm trying to remember if I have to throw out a ray or not. I don't think I do. So then what? What does that mean, though? Excuse me. That's the domain. That's not the domain of f inverse, right? I'm just saying the domain of. Sorry, I'm writing one thing and asking another. What's the domain of the log is my question. The answer is non-zero. You can take the log of any non-zero complex number, right? Of course, the log will be discontinuous wherever the argument has its degeneracy. So for the principal log, the principal log is discontinuous on the negative real axis, right? It jumps there from I pi to minus I pi for the imaginary piece. So that means I have to figure out when is this, right? When is this in the punctured plane, right? So what would that mean? So we have to figure out, we're looking for the condition w plus the square root of 1 plus w squared not equal to 0, right? That's the, we'd need that. So it's sometimes easier to think about, not about the condition you want, but about the condition you don't want, right? In other words, what don't we want? We don't want the square root of 1 plus w squared equals to what? Minus w. We can square both sides, right? And it is a highfalutin complex square root, right? But it's still the case that the square of the square root, principal square root, is still you get back to what's on the inside, right? I mean, that's still true. And the square of minus w is just w squared. Oh, that's troubling.
Back to the first line, I think it's still 1 minus w squared.
No, I'm quite certain it's 1 plus w squared. I'm pretty sure about that.
Why did we lose our plus or minus?
Oh, I picked one.
You should.
Yeah. You could put it, I mean, you could do this 4 plus minus, and this argument would still, what does this actually say then? Yeah, 1 equals 0. In other words, this is just, it's true for all w. Huh. So the range apparently of the sign that we're looking at hits everything. So then the question, of course, goes back to just sine of z. Like, how does that behave? Well, how does it map regions, right? So how is it periodic? So I have to go back to the sine z. So this wasn't terribly enlightening. I mean, it's not wrong to do what we did. It's just not. It hasn't showed me the answer yet. So sine of z is what? F of z is sine z. You notice that this is sine of what? Sine of z plus what? Plus 2 pi k, right? So sine of z is defined in terms of the imaginary exponential, which is 2 pi periodic, right? Integer multiple 2 pi periodic. So what does that look like? What's that geometrically? It's horizontal strips or vertical strips? What is it? In the complex plane. If I want to pick a domain for the sign on which the sign is injective, what do they look like?
Vertical strips.
Vertical strips of what?
2 pi.
Yeah. And I think that you're right with your comment, or you're in the right direction. So I have suspicion that what we're looking at is actually between minus pi and pi. I think it's probably the formula that I've written down there. My guess is that is in fact the inverse function for sine restricted to this vertical strip. My suspicion is that in fact is the domain for f on which we found an inverse function. So sine of pi and sine of minus pi both map to 0, right? Because sine of pi and sine of minus pi is 0. And let's see what happens with the rest. I think it's rather complicated, like how sine behaves. I think I have some pictures of it in the notes, but let's see here.
So it's not inclusive of minus pi and pi, it's just the region between.
Well, I was throwing them out, but let's see here. I can include one edge or the other, right? And I think I need to do that. Let's see here. If I include the pi, I think that would be, I would be tempted to do that because that's like the argument. But, I mean...
Don't you need this, the injective unsplit complex plane in your range, though? So that would map it to 0, so it wouldn't work.
Oh.
Because then it wouldn't be irreversible.
So, wait a minute. You're saying, what should I do?
I'm saying you wouldn't conclude that because it maps to 0.
Oh, they both
And
map.
your range is going to be...
Oh, right. Actually, excellent point. No, you're right on point, Nathan. We don't want to include that because what did we just decide? What was the one thing? Well, but, sorry. I forget. Are we talking about? Are we talking about the input, this thing here, or are we talking about the log? I mean, it doesn't matter what you throw at this expression, the circled expression, it makes it non-zero.
Oh. Yeah.
But I'm not talking about that right now. I'm talking about the domain of F.
Yeah. So isn't the domain of your inverse going to be the range of the regular function?
Yes.
Yeah, so that should be punctured complex plane, right? Because negative I log of w plus the square root of 1 plus w squared is our inverse function. And we found the domain of that is the punctured complex plane. So that should be the range of our inverse.
Well, that's the thing is, the function is not just log. The function is log of stuff. And the stuff undoes the badness of the log. I mean, it's like if I have cosine inverse, right, of 1 over 2 times x squared plus 1,
I see what you're saying.
you know, then the domain of this function is all reals.
So what you wrote there wasn't for f inverse, it was just for the log.
That's
Okay.
the, yeah.
Yeah, okay.
That's the confusion at the moment. So I guess I'm back to But as you can see, it's a more delicate question to figure out what actually is the domain of the function that you're finding the local inverse. I mean, I can find a formula for an inverse a lot easier than I can tell you exactly what is this the inverse for, as we're experiencing at the moment. So I think if you're lost right now, part of the reason you're lost is you don't know what the question is, right? So what is the question right now? We're trying to find the domain for f on which this formula is the inverse, right? Let's see here. And so this would be, this point in here I'm talking about is z. And then there's another picture here, right? F of z equals to sine z. And I think that this happens.
So in this case, we knew our codomain, and we're trying to find the domain that was injective to the codomain. And that happens because of what we found earlier, where for every w is an element c, where we did it for top right.
Yeah, that's why I think that calculation, to me, is what suggests that the range is everything. Is my suspicion. I mean, because the W, well, I don't know if the W, excuse me. Except for 0, right? Except for 0. Well, no, that's not right. 0 maps. I don't know. I'm sorry. I'm spinning my wheels at the moment, but I think we can claim success on having found this, right? But the question then of what's the range of this function is the better way to ask the question, right? If I know what's the range of this formula, that has to be the domain of the function. It has to be the restriction of the that's the function on the domain for the original sign, whatever the range of this is, right? What is the range of that? What are possible outputs of that?
Range of
this right here.
the range of that.
Doesn't that also have to be injective?
See, that's this. That's easy. I'm just making this too complicated, guys. It's not that complicated. Look, what's the range of this? What does principal log do? What's the formula for principal log? Principal log of stuff is equal to the natural log of said stuff, modulus, right? Plus I times the principal argument of stuff, right?
So it's any complex number?
So, right, this input hits everything except for 0, right? It hits everything except for 0.
But there'll
So,
always be stuff.
well, we've proved that this is not 0 over there.
Right.
So this takes on all values. So this ranges over all possible values. It takes all possible real values. And this goes from minus pi not included to pi, by definition of the principal argument. But after that's done, we multiply by minus I, which does what?
Rotates it a negative ln of stuff.
Yeah, it rotates it minus 90 degrees.
Arg of stuff.
So it takes the domain for the principal log, which is actually what? This. Right? That's actually the domain for principal log, right? You agree? It goes from minus pi not included to pi. You take that and you rotate minus 90 degrees. Shoot! It's that. That is the function which we're restricting sign to. I mean, the domain we're restricting sign, for which this is the local inverse.
So just to be
Sorry, I let you guys talk me into being confused there for a little bit. But
so just for
Mostly
completeness
Sharon.
of that though, you mean that your inverse function is injective on that range too, right?
I need I need to have solved for one thing, not for several things. So if I solve for one thing, it's injective. I mean, like the process of the solution I threw out.
So
that was the
solving
throwing.
for that already gives you the injectivity, so you just need to find the range.
That's throwing out the plus minus there is,
Yeah.
and throwing out plus minus, and selecting one branch rather than all branches of the little log is what guaranteed me the injectivity
Okay.
coming back. I mean,
No, that makes sense.
I'm selecting a branch, as it's called, yeah. But I don't know. I think this is by far the most challenging aspect of this course is this question of local inverses.
You said that about branch cut.
Yes, this is the branch cut. I'm not disagreeing with you, Sharon.